Hello again, everyone. Welcome to part 2 of our series on transformers in parallel. Last time we considered mismatched impedances. Today we will be looking at circulating current. And then the final video in this series will be all about how to change a transformer's vector group as far as the network is concerned without any modifications to the transformer wiring inside the transformer tank. So let's get going. Let's start off by considering a 33 kV to 11 kV transformer where the nominal tap is tap 7. Now, a typical transformer nameplate will have, amongst others, a tap position column, a volts column, and a current column. Question is why? What is the benefit of all this? Firstly, it must be stated up front that the voltage column does not give the HV voltage at a given tap. So, for example, it is not correct to say that on tap 3, the HV voltage is 34,651 volts and the current 416.5 amps. Indeed, the HV terminal voltage of the transformer is fixed by the source network and the volts drop across the transformer due to the load current and not the transformer tap position. Hence, the answer to the question is that from the voltage column, the turns ratio, or more correctly the voltage ratio, may be calculated. Please note that voltage and turns ratio differ when the transformer has a delta winding. They differ by a factor of the square root of 3. Before proceeding to circulating current, let's first take a more detailed look at the nameplate information and what can be derived from it. Firstly, the HV voltage increment per tap is 412 V. This is 1.25% of the nominal HV voltage. Indeed, it is common for transformers to have a voltage increment of 1.25% per tap. However, note that this is not the open circuit voltage difference per tap as measured at the LV terminals. Columns J and K show that the actual measurable increment per tap is not constant. It is only around 1.25% at nominal tap. However, as a rough approximate, 1.25% may be assumed at the LV side, particularly for tap positions close to the nominal. So, if we take the HV voltage at each tap and divide it by the nominal, we get the total boost buck range for the tap changer, which is minus 7.5% to plus 20% for this transformer, as can be seen in columns F and G. However, the actual boost buck range in terms of LV open circuit voltage given in column L is minus 7% to 24.9%. Right. Moving on, what is circulating current? Simply put, it is the current that flows between two or more transformers in parallel. We will restrict ourselves to only two transformers here. The current flows in opposite directions between the two transformers, as you can see here. The question now is, what causes the circulating current and what determines its direction? To start off, it is not caused by transformers of differing impedances. As we saw in the previous video, different impedances result in disproportionate distribution of the total current between the transformers, not circulating current. Circulating current results whenever there is a non-zero difference between the open circuit terminal voltages of the two transformers in parallel. So when CB1 is open, the open circuit terminal voltages V1 and V2 can be measured. If they are not equal, then circulating current will flow once CB1 is closed. If V1 is greater than V2, then the current flows from T1 to T2 on the 11 kV side. Note, this is independent of whether there is load current flowing through T1 and T2. How to calculate the circulating current? In principle, it is the LV secondary terminal voltage difference divided by the sum of the transformer impedances. If there is substantial cable impedances on the HV or LV side of the transformers, then these will need to be factored in as well. For our example, we will neglect cable impedance. Suppose T1 is on tap 12 and T2 is on tap 7, from the table we had earlier. We get from column I that V1 equals 11,731 volts and V2 equals 10,999 volts. Hence, the difference between them is 732 volts. Now, in order to calculate the circulating current, get that the Z base is 4.84 ohms at 11 kV. Hence, the ohmic impedance for 10% impedance transformers is J0.484 ohms, which we assume to be wholly inductive. From this, we can calculate the circulating current to be 436.6 amps at 11 kV. What about the current on the HV side? As you can see in column H, the volts ratio is different for the two transformers, and so the currents must be different on the HV side. From these calculations, the difference on the HV side is 9.84A. So how is this accounted for? Well, the source steps in and helps out, as you may have guessed. The table below considers the currents in the transformers and source for the example considered, as well as the tap changes at extreme positions. So we have that parallel transformers on disparate taps result in inductive current and hence VARs being drawn from the source. This phenomenon is used by system operators to regulate voltage on power systems under light loading conditions when charging current may cause excessive voltage rise. Now to test. So what I did was to simulate our very simple network of two transformers in parallel in the Power Tools for Windows Power Systems analysis software. T1 was put on tap 12 and T2 kept at nominal tap. Recall that tap 12 is equivalent to a boost of 6.2%, which is entered as minus 6.2% in PTW. This should yield an open circuit voltage of 11,731 volts. And that is exactly what we have here. 11,727 is close enough, I guess. Circuit breaker CB1 was then closed and the load flow rerun. We find here a secondary circulating current of 433 amps, which compares very favorably to the calculated value of 436 amps. Also note the nearly 10 amps difference between the transformer current on the HV side, and we can clearly see that the difference is supplied by the source. Interesting to note also that a 5-tap difference between the transformers can lead to circulating current equivalent to full load current of the transformers. Hence, overloading is a very real danger with circulating current, even though the circulating current is highly inductive, whilst load current usually has a high power factor. In other words, the addition of circulating current to load current is not a simple algebraic addition, but an addition of complex phasors. Hence, in a nutshell, there is a limit as to the use of transformers on different taps to regulate network voltage with low loading. In summary, circulating current flows between two parallel transformers if there is a non-zero difference between the open circuit terminal voltages of the respective transformers. 2. The circulating current flows from the transformer with a higher terminal voltage, usually one on the higher tap, to the other transformer. 3. The magnitude of the circulating current is determined by the sum of the impedances of the two parallel transformers. That's if we ignore the impedance of any cabling connecting the transformers to the bus bars. 4. Because of the voltage ratio differences, there is a difference in the circulating current on the HV side of the transformers. The source gracefully steps in and supplies the difference. 5. Hence, parallel transformers on different taps may be used for network voltage regulation. 6. Circulating current could lead to overloading depending on the connected load and the number of taps the transformers are apart. Okay, that's it for now. I do hope you enjoyed part 2 of Transformers in Parallel. Please do not forget to share, like, subscribe, comment, and press the notification button. Thank you until next time.